Okay, so in today's video we have this improper integral from 1 to infinity of the fractorial part of x divided by x raised to the 4th dx. Now I'm sure you have some questions. What is a factorial part of x? Well, factorial part of x is actually defined by the following formula. I'm going to write it right here. It is equal to x and then minus the floor function of x. And also here's another question I'm sure you guys are wondering. What is a floor function? A floor function is also known as the greatest integer function, where it denotes the greatest integer less than or equal to x. So for example, if we have that x is equal to 2.5, the floor function of that is 2. If I were to have pi equals x, then the floor of pi is 3. If I have the floor of negative 14.152, some sort of decimal, the floor of that is negative 15. Or another one, if I have the floor of 3.99999, then I repeat so on, its floor function of that is equal to 3. So now that we have that definition out of the way, so we're actually going to evaluate this integral. So with that, let's get started. Okay. So as stated, as the definition of a factorial part, it's equal to x minus the floor function of x. So this means I can actually just replace the factorial part of x with this equation. So 1 to infinity of x minus the floor of x, and then divided by x plus 4, or x raised to the 4th. Okay, now one thing that you should also pay attention is that the floor function will always be an integer. So the strategy to actually compute this, dx, the strategy to actually compute this is what we're going to do is we're actually going to break up the bounds of integration into smaller bounds. So that way when we do that, we can actually eliminate the floor function itself. So in this case, I'm going to actually rewrite this improper integral into a series of a summation series. So let me first write out explicitly what I mean. So another way to write this is, let's start with our lowest bound 1 and then to 2. So it doesn't matter whichever the closed interval between 1 and 2, anywhere from that, the lowest or the floor function of whatever I choose between the interval is always going to be 1. So I can replace the floor function for between these bounds with x minus 1 divided by x to the 4th dx. Okay, and then plus, and now we're going to work our way from 2 to 3. Then choose any x in between the interval 2 to 3. Take the floor function, it'll always be 2. So I can replace the floor function from this bound with 2 divided by x to the 4th dx, and then do it again from 3 to 4. Then I would have x minus 3 divided by x to the 4th dx, and then so on and so forth. Okay, so everything's so now if you're noticing a pattern, we can actually create a summation series. So I can actually write as the series from k is equal to 1 to infinity of the integral from k to k plus 1 of x minus k divided by x to the 4th. Okay, and to simplify this a little further, I can actually split I can split into two fractions. So we have same n is equal, or k is equal to 1 k to k plus 1 of x divided by x to the 4th, which is just 1 to the x divided by 3, and then minus k divided by x to the 4th in dx. Okay, now we can calculate this definite integral easily. So I'm actually going to rewrite this a little bit so that way we don't have a fraction in our indefinite integral, but simply we just have the function x raised to a negative exponent. So let's just ignore the summation for now and let's calculate the definite integral. So it's from k to k plus 1 of x to the negative 3, and then minus k times x to the negative 4, and then dx. Okay, sweet. So when we take the integral of x to the negative 3, so it's plus 1, negative 2, then divided by negative 2. So we have, let me actually change, when we're evaluating this integral, let me actually change the different color. So this is going to be, negative 1 divided by 2x, and then negative 2, so 2 divided by 2x squared, and then minus, let's see, plus 1, then divided by 3, so this will be a plus, and then this will be k divided by 3x to the 3, and then we're evaluating this from k to k plus 1. Okay, nice. And then we can just substitute, just integrate, and then we can just evaluate through our bounds. So we have, let's see, it's negative 1 to 2 times k plus 1 square, and then plus, let's see, 3k plus 1 cube, and then k, okay, and then minus, everything is just k here, so negative 1 to divided by 2k squared, then plus k divided by 3k cubed. Okay. Now we can actually simplify this further. What I'm going to do now is I'm going to find a common denominator for these two. Okay. So let's see. We multiplied the denominators. So this is okay. So if I multiply 3k plus 3, so this is negative 3k plus 1 cube, then plus 2k k plus 1 square, and this is being divided by 2 times 3, so that's 6, and then they have the same base, so this is k plus 1 to the 5th. Okay, and then over here, so this is negative 3 cubed, and then 2k squared plus k, so this is plus 2k cubed, and divided by this is 6, 2 times 3, and then 6k to the 5th. Okay, so far so good. And I can actually factor out a k plus 1 square from the numerator. So this is, this ink's running out, so I'm gonna have to go back to pink. So what I say, okay, this is factor out of k plus 1 square. Okay, and this will be, let's see, this is k plus 1, so this is negative 3 times k plus 1, and then plus 2k, and then this is divided by 6k plus 1 to the 5th. We can simplify that even further. K plus 1 square, and then this k plus 1 to the 5th, the numerator will cancel, so we're left with the exponent of 3 on the denominator. This is 6 k plus 1 to the 3, and then this is negative 3k plus 2k, which is negative k, and then negative 3, so this is minus 3 over here. Okay, so this is our value for this expression here, and then minus, so we have negative 3k cubed plus 2k cubed, which is negative 1, negative k cubed. So instead I'm actually, and then when you distribute the negative, it becomes positive. So I'm gonna change this sign to a positive, and this will be k cube, and then this will be k squared in the bottom, since the k cube will cancel out. So this will be 6k squared, and then 1. Let me make sure. So 3k cubed plus 2k cubed, or negative, so this is negative k cubed. K cubes cancel out, so this is negative 1 divided by 6k squared. Then distribute the negative, you get a positive. Okay, cool. So this is our answer to our definite integral over here. So now we can actually substitute back. So we have, and I'm actually going to, because this is commutative under addition, I'm actually going to move this to the front and this to the back. So summation is, let's see, let's say k is equal to 1 of, go put this in brackets. So this is 1 over 6k squared, and then distribute out the negative. So then now this will be k plus 3 divided by 6k plus 1 cube. Okay, and then I can actually factor out a 1 over 6. So this is 1 over 6 multiplied by the summation. K is equal to 1 of where is it? Okay, so this is 1 over k squared, and then minus k plus 3 divided by k plus 1 cube. Okay, so far so good. So pay attention that the summation from 1 over k squared, this is actually a special series. This is known as Basils Problem. So this definitely converges by the P-series convergence test. And this actually in fact converges to pi squared divided by 6. So now with that, I'm gonna write a little note for this in particular. This is Basils Problem. Okay, so that means we have, yeah, I'll write it here. So we have 1 over 6 multiplied by pi squared divided by 6. And then multiply the 1/2. I'll just write it down here, why not? So that means this will be pi squared. This will be pi squared divided by 36. And now we have one more summation to calculate. So this will be 1 over 6 multiplied the summation. K is equal to 1 of k plus 3 divided by k plus 1 cube. Alright, cool. So far, okay, that's awesome. Okay, now now that we have that, now let's actually focus on evaluating this summation here. So let's just ignore the 1 over 6 and let's just focus on the series over here. So left to calculate is the series from k is equal to 1 to infinity of k plus 3 divided by k plus 1 cube. Okay, now I can actually split this into two summations because it's a fraction. They share the same denominator, so we can actually write this as let's see, k is equal to 1 to infinity of k divided by it's supposed to be parentheses before the k. This is k plus 1 cube, and then plus the summation of 3 divided by k plus 1 3 or k plus 1 cube. Okay, nice. Now here's the next strategy I want to do. What I want to do now is I actually want to readjust the index of our summations. This will make simplifying to our getting our final answer a lot smoother and easier without any sort of complications. So what this means is I'm actually going to change, instead of k is equal to 1, we're actually going to start with the index at k is equal to 2. So when I start at k is equal to 2, so let's see, when we have k is equal to 1, so this will be 1, this will be 1, and then this will be k plus 1 plus 1 is 2. So definitely denominator will be k cubed, and then this will be k minus 1 in the numerator. And then same thing for the other one, plus this will be k is equal to 2. So numerator doesn't change, it's still 3. And then let's see, we have k equals to 1 here, so this is k plus, or 1 plus 1 is 2. So this will be just k cubed. Okay, nice. And again, a second time I can actually split this piece into two series again. They share the same denominator. So again, now we have three different series to calculate. K is equal to 1 of k divided by k cubed, which is just 1 divided by k squared. Or this is actually supposed to be, the index is supposed to be 2 over here. Okay, and then minus, let's see, infinity, k is equal to 2 of 1 divided by k cubed. And then, let me rewrite that again, roll my 3 too big. Okay, and then we have plus series from, let's see, infinity, k is equal to, did it again, it's supposed to be a 2, not a 1. Remember, we adjust our index, and this is supposed to be 3 divided by k cubed. Okay, now, notice that just from before we calculated, calculated that, well, not really calculated, it's by fact that the summation from k is equal to 1 to infinity of 1 over k squared is equal to pi squared divided by 6. Be careful though, because now that our index is at k equals to 2, so that means we actually have to subtract a piece from when k is equal to 1 of this series. So obviously we know the infinite series for this, from k is equal to 1 to infinity, is equal to, let me see if I can write this in black, just so say something. Okay, so okay, let me do this first. Okay, this will be evaluating 3 different series, so I'll just write this like so. Okay, so we know that the infinite series from k is equal to 1 to infinity of 1 over k squared is equal to pi squared over 6. But we need to subtract a piece when when the fraction is being evaluated at k is equal to 1. So when we plug k is equal to 1, it's just 1 over 1 squared is just 1. So that means it's this series in particular is actually equal to pi squared divided by 6 minus 1. Okay, that's 1 down. Now we have to evaluate this series here. So we have the summation from k is equal to 2 to infinity of 1 over k cubed. This series is actually very special. This is actually the formulation is actually known as the Riemann zeta function, and the function is actually defined as sigma of s, which is equal to the series from n is equals to 1 to infinity of 1 over n s. Okay, this function is actually pretty important in analytical number theory, but it's also used in complex analysis, since the Riemann zeta function is a function of a complex variable with the complex variable s in particular. So this means in this case we have that s is actually has to equal to 3. So, but I shouldn't say so, but again, we have our index is k is equal to 2. So just like before, remember it's defined from the infinite series from n is equal to 1 to infinity, but we have that our index k is starting at 2 to infinity. So we again have to use the same strategy like what we did last time and subtract a piece when k is equal to 1 of the series. So this we know is the Riemann zeta function at s is equal to 3. But we need to calculate what when k is equal to 1 and subtract that. So this is 1 over 1 cubed, so this is just minus 1. And then the last one is, again, the same thing as, very similar as this piece here, except we have a scalar of 3. So what I'm going to do first is I'm actually going to move out the 3 outside. And then this is the same thing as it's the same formulation as the Riemann zeta function. So this is from the zeta function s equals 3, but then k is equal to 2 to infinity. So we have to calculate our index, and when k is equal to 1 and subtract that from there, which in this case it's just -1. Okay, cool. Now that we have our pieces, now let's assemble everything together. So this means we have that means the summation of this piece is equal to pi square over 6 minus 1 minus the Riemann zeta of 3 minus 1, and then plus 3 times the Riemann zeta of 3 minus 1. Okay, so that means we're just gonna put everything together. So this is, let me actually multiply the 1 over 6 to here first before I do anything. So this is 1 over 6, then multiply by pi squared divided by 6 minus 1. And then this is what, minus zeta 3, then that's a plus 1. And then plus 3 times the zeta function, and s equals 3, and then minus 3. Okay. Okay, so now now all we have to do is just multiply the 1 over 6 into our expression inside. So now we have that, so we have pi squared divided by 36, then -1 plus 1s, they cancel out, minus zeta 3, then plus 3 times zeta 3, that's positive 2 zeta 3. So this is what is it? This is plus 2 divided by 6, so this is zeta 3 divided by 3. And then we have minus 3, so this is minus 1/2. Okay. So our summation here would multiply with 1 over 6. This is equal to our expression here. So now the last thing left is to take pi squared divided by 36 and subtract it from here. So pi squared divided by 36 minus pi squared divided by 36, then plus zeta of 3 divided by 3, then minus 1/2. Okay, well, clearly pi squared divided by 36, these two terms cancels. Then we can just distribute the negative. So this is negative zeta 3 divided by 3, and then positive 1/2. So I'm actually going to move the 1/2 into the front. So this means we have 1/2 and then minus zeta of 3 divided by 3. Okay, and then therefore we can conclude, I'm gonna write this in black, our conclusion. Therefore, the integral from 1 to infinity of the factorial part of x divided by x to the 4th dx is equal to 1/2 minus the zeta of 3 divided by 3. It's pretty cool, right?